Okay, welcome everyone. So I'm presenting work that we did in conjunction with Penn State University and Annual and Guangzhou University in China about model-based optimization of a campus district cooling system. So first I'm going to explain quickly the background and the motivation for this work, and then explain how we modeled the system and present the actual case study afterwards with some optimization results, and finish with some concluding remarks. Regarding the motivation, why we look into district cooling, and one of the key drivers is that space cooling is one of the fastest growing energy end use in buildings. And there's very little work that has been done in analysis and simulation of the district cooling system. So if you look at the literature, there's a lot of work being presented about district heating, but very little about district cooling, which has a few unique features that I thought would be interesting to look at, and also put together a set of tools so that other researchers and engineers can start analyzing and improving the design and operation of those systems. So the objective of that work was to demonstrate how Modelica can enable a complete district cooling energy analysis. So in fact, this complete, we mean all the way from the chilled water plant to the distribution and then the buildings coupling. That includes then the thermal analysis, fluid flow analysis, and also the controls, detailed controls design and simulation. We applied that to identify investment-free energy efficient strategies for an actual case study building, and evaluated the carbon and operational cost savings for that particular site. So the site that we were selecting is part of the University of Colorado in Boulder. So it's a campus of which we picked 6 buildings that are connected to this district cooling system. It has a peak load of about 2.5 megawatt cooling loads, and roughly about 1.5 kilometers of pipes. So the system is shown here, where we have basically this main central distribution of the pipe, and then the individual buildings are connected to that radial distribution network. So the chilled water plant, or the central plant, consists then of 2 single compressor chillers. Each has about 2.5 megawatts. So there's a redundancy in this system here. There are 3 chilled water pumps that consume about 30 kilowatt each, and then also 2 condenser water pumps that have about twice the installed electrical capacity or connection power. There's also a non-integrated waterside economizer that you see here next to the 2 chillers in the central part of the schematic. A non-integrated, it basically means that the economizer is parallel to these chillers, and it can operate then in conjunction with the chiller, but it's typically a little bit less efficient compared to the integrated waterside economizer. But this particular plant has a non-integrated waterside economizer, and then also 4 cooling tower units that reject the heat from the condenser to the atmosphere. So in terms of modeling the district cooling system, the first step was really to understand the system schematic, and then build a top-level model that characterizes then or connects the central plant, the distribution network, and then also the building load. And in the next few slides, I'm going to explain then how we modeled the individual components of this district cooling system. So starting with the central plant, you can probably recognize here the system schematics that's shown on the lower part. And this one is now one part that we implemented in the central plant icon using the hierarchical modeling of Modelica. And one of the benefits of this approach is that with Modelica, you actually see one-to-one correspondence between the actual real equipment and then the corresponding model implementation in Modelica. So if you recognize the icons, which I hope they are big enough on that screen here, you recognize, for example, the individual, the chillers, and also the cooling tower, and the implementation of them is then done again hierarchically. For example, if you open the icons with the cooling tower, you see then underneath the cooling tower with the bypass. And if you further open that up, you see then an array of cooling towers, each with a shut-off valves. And we have an instance of 2 of these cooling towers to represent the actual implemented system. A similar approach is then done with the chiller and the water-side economizer, which is in parallel to these 2 chillers. So on the left side, you see the heat exchanger for the water-side economizer, and then on the right side, the actual iconic implementation of the chiller. And if that's being opened, you see then the actual underlying chiller implementation, which again, we used an array here of 2 chillers to model that part. In terms of the cooling mode control, so there are 4 modes of controls implemented here. So on the very left side, you see the supervisory control. This one sets the cooling mode of operation. That's being input to a staging control that stages the chillers and water-side economizers and also the pumps. And then there's a subsystem control that controls the individual subsystems here, and then the local loop control is primarily concerned with tracking set points from the higher level control. To implement this hierarchical control, we implemented a finite state machine, or state graph, sometimes called, for the mode switching. And the approach for that is then in Modelica that you have these different states, and shown in white here in the Modelica implementation, and then the state transitions shown in black. And you can put the condition on the state transition that if this transition is true, you move from one state to the other state. And this transition is typically, for example, differences in terms of measured versus measured variable versus set point. And you can also easily add a timer that a certain condition needs to be satisfied for a certain duration. And if that's true, then you move to the next state. And this state graph of finite state machines, they are very convenient then to implement these different modes of operation, and allows them to visually display and also debug how you move from one operation mode to another. So that's, from the modeling point of view, something quite powerful here that's supported via the Modelica standard library. Then for the chiller staging, there's again a finite state machine that we implemented here that switches then between no chiller operation, operating one chiller, or operating the second chiller. And then moving to the distribution network, that's a core component that we're implementing now for an extension of the buildings library for this, to better or more conveniently simulate the strict cooling system and the strict heating system. But the key part is this distribution network that we can then use to model loads in a vectorized form. So you can have as many loads connected to this distribution system. And then this model itself is then embedded in the pipe models for flow friction. And you can also replace these pipe models, for example, with models that also model the transport delay and may have coupling to the ground heat transfer. So if you open this icon, you see then underneath the connection with the 2 pipes and the flow junctions. And this one is basically used again to hierarchically set up those distribution network and allows them to relatively quickly parameterize the distribution system. Then connected to this distribution network are the energy transfer station. In this particular example, we implemented a very simple energy transfer station because we had measured the loads from the different substation, and the approach here was to have an ideal heat exchanger that just extracts that number of or that capacity out of the fluid stream, and it regulates then the water stream that's being fed through this energy transfer station. In terms of the model validation, we compared the coefficient of variation of the root mean square error and then also the normalized mean bias error. And there are some ASHRAE tolerances published that indicate acceptable range for the validation. It's about 7% for the coefficient of variation of the root mean square error. And for the normalized mean bias error, the acceptable range is about plus minus 10%, and all the validation results are within this bound scale. So we have relatively high accuracy for that particular model. So having done the model creation and the validation, we looked then into how to optimize the operation of this system. And there were a few criteria where we can start doing optimization in terms of the condenser water supply temperature and also the flow rate to the condenser. And then also the operation of the water side economizer, which implicitly depends then on the condenser water supply temperature via the control of the staging of the individual components. So to do this improvement, we set up 3 different optimization problems and looked at them individually, one after the other. So the 3 approaches that we looked at, all of them try to minimize the electricity consumption for the chiller, the cooling tower, and the pumps. The first problem is the simplest one, where we have a constant set point. So we try to figure out what's the condenser water temperature that minimizes the electricity consumption, assuming we're going to use the same temperatures throughout the whole year. The second formulation uses a fixed approach temperature, where we basically use the web pulp temperature and then optimize the offset from this web pulp temperature and use this web pulp temperature plus the approach temperature as the set point for the condenser water temperature. And the third approach is then one level more of complexity, where we also have a correction then for the part load ratio of the chilled water plant. We basically try to adjust that also depending on how much load we have on the chillers. So during the optimization, we consider the baseline that has no optimization of these quantities as using 100% and of the energy consumption. And if we use a fixed set point temperature for the chilled for the condenser water temperature, we have savings of about 2.5%. And the other 2 optimization approaches, where we offset the condenser water temperature based on the web pulp temperature or based on the web pulp temperature and the part load ratio, we have savings of about 4.5%. During the optimization, we then also displayed then different key performance indices. So in terms of site energy consumption, where we have again baseline in white. Then we did one simulation where we have no water side economizer, which of course increased then the energy consumption here over a year. And then in green indicated here are the 3 optimization results. So with the fixed set point for the condenser water temperature, then the fixed approach temperature, and an adjusted approach temperature that also takes into account the part load ratio. And all of them have significant savings there in terms of site energy cost and also peak power reduction, as well as CO2 emissions. Then having done this optimization, we also looked at the individual energy consumption of the different components. And what is shown here is that the condenser water temperatures shown in orange have a very large energy consumption if you compare this one to the consumption of the chiller and the cooling towers, for example, which are shown in black and in bright blue. So in the next step, we are interested in further reducing the energy consumption by adjusting the flow rate of the condenser water temperature. Yeah. And we looked into the 3 variations. So in orange, first is to have one condenser water pump operating at the full load. So that was similar than the base case design. Afterwards, we reduced the flow by about 25%. So that's the middle one of these orange plots. And in the third approach, we used then 2 condenser water pumps, each with 50% of the capacity that the case before had. And this one was the best operation in terms of the site energy consumption and all the other key performance indices. And once we reduced then the flow rate, we did again an optimization using now the fixed approach temperature, which is somewhat simpler than the fixed approach temperature that's also adjusted based on the wet pipe temperature. And that gives overall then the most savings here of the energy consumption and of the other peak performance indices. So shown in dark red here are now the optimal result here, where we use the middle of those three optimization because it has lower complexity and has almost the same performance as the higher complexity optimization. And we reduce the flow rate of the condenser water pumps. So in conclusion, we developed these open source models for the Billings library for district cooling systems. They should become available next spring with the official release of the Modelica Billings library, but the models are already available now as part of the development branch. And the case study shows that there are about 15% reduction in energy consumption and in CO2 emissions, and about 9% reduction in costs without any upfront investment that will need to be done here. If you like to see more details about that, please come see me or look at the reference that's cited here that has a lot of the background information of this case study. I'm very happy to answer any questions. This one is, I think it uses the electric EIR model or electric EIR reformulated, if I remember right, yeah, based on datasheet. But it's always quite a challenge to get those chiller performance data correctly, because usually manufacturers, they have a very narrow range where performance data is being published.
But on those, the fixed approach really the same more advanced approach? Was that still relevant?
I think it's a coincidence that we have the same savings. If you look carefully in the peak energy consumption, there is a slight difference between them. Yeah, but then overall, over the annual energy consumption, it turns out to be the same within 2 digits. Yeah. So I can repeat again, please. It's a data feed based on the data that we got from the actual installation. It's basically a shut-off valve. So there's a state machine implemented that then decides when we switch the chiller. And when we switch the chiller, there's a shut-off valve that restricts then the flow rate through that chiller. So if you're looking at the schematic diagram, go back here. Yeah, I see. Oh, there's some delay here. Okay. Yeah. So the chilled water pumps, they are all in parallel, but then the individual chillers then shut off valve. So if the chiller is not operating, we close that valve, and so that must be the flow rate. That is no flow rate to the chiller if it's switched off.
Okay, I have a question. So for the district cooling system, based on my experience, the heat loss around the distribution system cannot be like that.
Mm-hmm.
So I'm just wondering, how do you do the calculation for dissipation from the pipe?
Yeah, to be honest, we need to look into the detail again, how it's modeled, in particular in this case study here. But we do have now models for the soil temperature, and typically it's a lot of hand waving how to do that properly. But if it's insulated pipes, you typically model then insulation, and you can always model part of the soil and then assume undisturbed soil temperature if you're far enough away. That's reasonably accurate, I think, for this typical discrete cooling system. For some of the fifth generation combined district heating and cooling system, that's still a bit of an unsolved problem how to do it best, because they have typically pipes that are non-insulated, and you actually want to exploit the heat transfer with the soil. So I think a good approach there, or so far, is to use radial heat conduction to the soil, but it's a bit an open question of how far do you want to go into there, because it's not purely radial, the heat conduction, because at some point you start exchanging heat with the surface. So you would need to have some more sophisticated methods that, to my knowledge, are not available yet in those system simulation. And 3D analysis or 2D heat transfer analysis would be prohibitive. Yeah, I think that's a bit of an open research or task to implement that.
Okay. So basically, we now have a model to look like this. To model this heat extraction.
It has it for radial heat conduction from the pipes to assuming some radial heat conduction into the soil. So that's something that we can model. We also have a model for undisturbed soil that you can use the boundary condition here. But this one assumes now radial heat conduction, but the pipes are typically maybe a meter below ground. So that the radial heat conduction is an approximation. I think to get some higher accuracy would be interesting to see how we can come up with a method that actually takes into account the heat exchange also with the surface. And just on top of my head, I would probably start looking into how gradient ceilings are computed with this efficiency based on the temperature distribution that we have among those pipe plane. I think that might be one approach to start combining those two methods. But that's really, it needs more work to implement.
Okay, thank you.
And maybe just for clarity, I mean, we do have models now also where we can model the heat capacity of the water in the distribution pipes, which can be quite considerable dynamic effect, in particular if you change the supply temperature. So those models are in the ARIPSA library and in all the 4 libraries that depend on the ARIPSA library.
Thank you, Dr.
Thank you.
Good afternoon, everyone. My name is Charles Pan from the University of Texas at Dallas. Today, my presentation topic is the hybrid MPC of chiller plant with thermal energy storage and evaluated with the Modelica Python code simulation. First, I will introduce the background and the motivation of this study and the challenges and our proposed work to solve these challenges. Then I will introduce the chiller plant with the water storage dynamic model on Damola based on Modelica language. And then we build a conformity modeling using data-driven model with improvement linearization and the model selection to reduce the complex. And again, we designed a hybrid MPC for demand response operation, and the simulation study with Python Modelica code simulation is shown at the end. Yeah, currently, about 40% energy is used by buildings in the United States. In the meantime, building operation consume about 75% electricity. So the demand response becomes more and more important. To deal with the demand response for the chiller plant, there's 2 key changes. First, if we want to optimize the chiller operation, the significant nonlinear is the big issue. And on the other hand, the continuous and discontinuous issues due to the on-off or the model switch. Some existing solutions contain the conventional schedule techniques and some load shifter with thermal energy storage. Some work, some current work is on the mixed integer linear programming MPC strategy with piecewise linearization or do the mix the integer and MPC in different layers or hierarchical. So our proposal is to try to optimize the mixed integer program globally. So we propose a workflow as we build a chiller plant with some energy storage system first, and then we collect the data from the Modelica simulation and build a data-driven controlling model with equipment operators for different operation modes. And then we design the hybrid dynamical system with model switch, which let the program become a mixed integer binary programming optimization program. And then we design the MPC based on two targets, temperature regulation and power minimization. And to solve the mixed integer binary programming, we use a complexification method to make the binary program into a mixed integer linear program to facilitate the computing speed. So the simulation plan includes a chiller plant model, a water storage model, and simplified the building energy model where the cooling load comes from the energy plus data. There are two inner PI controllers for this system. The first one is using the EV opening to regulate the superheat, and the second one is use a compressed speed to regulate the evaporated living water temperature. There is a thermal layer for the subsystems, which is the chiller and the stratified some energy storage based on the tier library and building library. So the integral system has two working operation modes. The mode one is the TS charging mode. The TS charged by chiller water from the chiller plant, and the building load handled by the chiller water from chiller plants, and the building return water and the TS outlet water mixed and then return to the chiller plants. The model 2 is the TS discharging model. The TS discharges chiller water to HU. The HU supplied chiller water comes from the chiller plant and the TS, and then the HU return water going to the TS and the chiller plant together. So as a model-based control, like MPC, we need a controlling model for the integral system. So here we design the data-driven model, and first we select the states for dynamic states for this controlling model. For this study, we select 6 states. There are 3 states related to the chiller plants, which are the compressor discharge pressure, the compressor discharge temperature, and the compressor suction pressure. And a state related to the building load issue related states is the chilled water return temperature. And two in the strategic thermal energy storage model, we use 2 layers models to represent the system, the subsystem. So there are two temperatures, including the top layer temperature and the bottom layer temperature. Now for the inputs, actually, we select the input including the tower fan speed, the chilled evaporated living water temperature set point. The second input is related to the compressor speed by the PI controller. And the last input is the chiller evaporated water mass flow rate. And additionally, we will use model switch input data as as integer input 0, 1. 0 means the model 1 and 1 means represents the model 2. And in the disturbance side, we have two disturbances, the ambient temperature and the building load. The total power contains three parts, which come from the compressed power, tower fan power, and the evaporated liquid pump power. To deal with the nonlinear system, we use a linearized method with the equipment operators. So first, we have the original state and the input and the disturbance. We can build a discrete time dynamic system, nonlinear dynamic system as this equation. And by the idea of the equipment operator, the nonlinear system can lift into an infinite dimensional function space to linearize the nonlinear system. And in practice, we usually use a finite dimensional lift space. Here is the observer for the nonlinear system, which where the Z represents the canal functions, and it can be user defined. So in this study, we select the original state X lift into the first order, second order, and the cross terms with these states. So the final lift state is the Z instead of the X. And to identify the coefficients, we use the sparse identification of the nonlinear dynamics with control method, where it uses the lasso algorithm to identify the coefficient. With the help of lasso, we can identify the no important kernel functions coefficient as 0. So to determine the accuracy and the simple of the identified model, we use the archaic information criterion to determine which model is the best choice. And this information criterion means the trade-off of the model accuracy and the model complexity. And also the total power model for these two modes is identified as a map of the lift states and the inputs and the disturbance. So here is the identification results. The blue line is the data from the simulation, and the green line is the identification model. Although the matrix A may be large because we have tons of the lift function of X, but actually after with the help of the model reduction, about half elements in the A is actually 0. And this is the model selection results for the model 2. And with these models of different modes, we can build a hybrid system model by mixed dynamical system. So here we use additional input data to represent the model switch into two modes. So therefore, the total dynamic can be represented as one equation, and the output of the power is also right in the equation. So now we can find the integral system becomes a mixed integer dynamic model with a binary term like the z times delta, u times delta, and w times delta. The next plan is to design the hybrid MPC for this mixed system. So for this MPC, we have two targets. The first one is minimize the energy cost, and the second one is regulating the HU return water temperature. So here in the cost function, we have two terms which represent the temperature regulation and the energy minimization. The C represents the electricity rates, and it times the power in the energy cost. And for the constraint of the system dynamics, actually the output of the y can be substituted into the function. So the cost function can be will be projective programming with mixed integer bilinear terms. To solve this mixed integer bilinear programming optimization program, we proposed complexification for this bilinear programming. And first, we define the new variable for the bilinear functions, the fz instead of the z times delta, and fu instead of the u times delta. We ignore the w times delta because we assume the determinant is no variable in our system. So actually, there are no value. So, here with these new variables, we can build a convex envelopes for these two variables, and it requires we use the McCormick envelopes to build this convex program. Now, with additional constraints, the mixed integer bilinear programming became a mixed integer linear programming, and which is capable to facilitate the computational speed. And in the simulation study, we built a co-simulation platform with the FMI, where the FMI is output from the Damona, and the Python is used to code for the MPC controller, and then they can do the data exchange in simulation. And in the simulation setting, the sampling time is 600 times, and the prediction horizon is 2 hours. For the co-simulation, we use the Python package like the convex programming, the CDXPY, and the FMPY for the co-simulation. And this is the co-simulation results for the hybrid and PC operation. The first variable is the model switch decision delta, which one is the TS charging, and the 0 is the TS discharging. So the second variable is the electricity rates, and roughly we can separate the electricity rates as 3 regions, which are the low price region, medium price region, and the high price region. We can find that in the low price region, the model switch is dominated by the cooling rate, cooling load disturbance, where when the cooling load is low, the motor is became the TS charging around the 5 hour, and when the cooling load is higher, in between the 2 and 3 hour, we can see the TS is discharging here. But in the high price region, no matter the cooling load is lower, like around the 19 hour, but the TS is still discharging because it can save the energy cost. And the blue line is the output from the controlling model, and the red line is output from the co-simulation. And there is some oscillation because between the model switch and the inner PI controller at this point. And another regulatory target is for the actual return water temperature. And this is the input, optimize the input and the total power. The blue line is calculate total power by the controlling model, and the red line is calculated by the co-summation. And the main total power of the blue line controlling model is 288 kilowatts, and for the co-simulation is 252 kilowatts. And in conclusion, we propose a data-driven model method of chiller plant coupled with the water storage, and the CDC-based Goodman evaluation model are identified with simulation data from the Modelica based dynamic models. And mixed integer bilinear programming and PC formulates for global optimization of the energy saving and the satisfy of the cooling rate demands. And to solve this problem, we use convexification with the McCormick envelopes and transform the problem into a mixed integer linear program. And finally, the proposed control strategy is evaluated with the Python-based co-simulation framework. So thank you. Any questions?
It's my first time to see operation to your system. So my question is that operator is to add the national as like and the next question is that how do you get the intention emission for the
First, it's a data-driven model, and you connect the data. And again, for the program operator, is can be user-defined kernel functions. It depending on your choice. You can trace, for example, in my study, I traced at the maximum of the signal order of the original state, and maybe you can choose more. And also maybe you can use a cosine, sine function, anything you can use. And then I use the Cindy to do the model reduction because for the you choose the kernel functions. Some nonlinear maybe is not important. It can be zero. The coefficient can be zero. So there's a certain way to determine which need to be zero, and it can reduce the complex of the model.
And the say is the dimensional nonlinear system.
Yes, yes.
And is there any figure to show the difference between your new system representation and your original system?
These are the compare with the original data and the fitting model. Maybe the figure is not very clear, but that actually there's two lines. There's a blue line and the green line. Because our data is from the simulation, so sometimes it's kind of very good. But if you use in real time, there will be some change to see some difference here.
So that means your nonlinear system could be represented by limited dimension, right?
Yes.
Okay. And my question is that with this method, the operator to the order of the system more computation, less computation the original method, like the AI model to that the nonlinear system. What's the difference?
Actually, we use this method to nearize the nonlinear system. So if your system is too nonlinear, then it requires a linearize it is helpful. But if your system just have few nonlinear function, it depends on your system. I cannot to answer here. Yeah. Yeah. Uh, I cut off the initial logs at the beginning to do, we found the initial data to stable the system, and then we added the disturbance. And for the plot, so I just show after when we added the disturbance here. Oh, you mean the beginning? There's a difference here, right? Yeah. It's due to for the converting model. Actually, we use a few equation to represent the total system. So it will be always when you use few equation, there will be some inaccurate in the model loss. So it always happens. It cannot be, in my opinion, it cannot be always perfect. And yeah, there needs some future work to do the approximation and to find out maybe a better way to represent the total system. Because in the diameter of the total system, maybe have 100,000 equations, and we just use few equations here to represent the system dynamics. Yeah. Yeah.
I saw you use sometimes use the two-layer model.
Yes.
That's wondering if you have tried with like the 10 days model, and then use like a digital model to learn that field. You could tell or something.
Yeah. Actually, I consider it as accuracy and complexity of the balance, because if we consider more layers, then the space will become more, and it may lead to higher space to linearize the model. So, but we can try to see if the model cannot be good as we think. We can try. Yeah. Thanks.
Okay, everybody. Thanks for the nice introduction. I'm David Blum from Lawrence Berkeley National Lab, and I'm just going to talk today about the use of Modelica and the functional mockup interface for the building optimization testing framework. Really just overview this project, which is nicknamed Bot Test here. And I just want to acknowledge that the funding that our team especially received was from the DOE. And the project's also in collaboration with a number of institutions, including other national labs, PNNL, NREL, Oak Ridge National Lab, and then also development within the IBIPSA Project 1 over the last 5 years within Work Package 1.2, and you can see the website there for more information, and really a host of a large amount of people who contributed to this project. Tried to list everybody that I could. Some people have kind of changed institutions since Project 1 and recently, but really this is a large effort. And so a big thank you acknowledgement to everybody who's part of the project. So what I'll do today is just start with an introduction, giving motivation and context to the Bobtest project, and then I'll go through just an overview of the framework components. I'll give a couple of examples in terms of its usage, and then offer some conclusions and next steps for the project. So to give some background and context, with HVAC systems in general, we're seeing, I say, sort of future additional requirements. So in addition to providing comfort and safety to occupants within buildings, obviously we want to start reducing energy and carbon, or reducing energy consumption and carbon emissions. We want to integrate with electric grids, for instance, responding to demand response signals, or responding to, or doing load shifting in response to, say, dynamic electricity prices, or providing more resilience in case things like storms or other natural disasters are occurring and buildings need to sort of change their operational states or operational objectives. So what's really happening with these sort of additional requirements is there's a growing need for improving controls for energy management within buildings, and in particular, in response to dynamic operating conditions and objectives. So the question that we've sort of asked ourselves is what new tools then are needed for the new development and adoption of these new control strategies and methods. So when we look at controls development sort of in the building space, you can see in the upper right there a number of advancements that have been studied and made over the years, including advanced rule-based control, for instance, through ASHRAE Guideline 36, model predictive control, which we've heard a lot about this week, or also data-driven control, things like reinforcement learning, which is really starting to pick up also in the buildings industry. So there's a lot of promise to these different control strategies to address the sort of objectives that I mentioned before, but there's some challenges still in evaluating how well they perform on different case studies. And the first challenge is that a lot of the studies that are done with these new control strategies are individualized. So when you sort of read the different studies or different buildings, HVAC types, climate periods, and even performance metrics that are used to evaluate the control strategies. And you can even have different comparative baselines sometimes. So for instance, this plot on the lower right is a study that we did not too long ago where we evaluated different control strategies applied to the same system, the same building. Although I mean, what you're seeing is kind of a lot of some parameterization of climate and say internal loads and things, but along the y-axis are basically different control implementations, different control strategies, and on the x-axis, what you're seeing there is HVAC consumption. And basically what I'm trying to illustrate here is it matters what control strategy you use in terms of how much energy your building consumes. And so if you're evaluating a new control strategy, then your baseline, what you're comparing to, basically makes a difference. So all this kind of constitutes in this challenge of it being difficult to identify which approach is most effective sort of in which situation, because you don't really have these apples to apples comparisons between different approaches. The second challenge is that the setup time and effort for really good case studies can be large. So if you're using a real building for your case study of a new control strategy, then that obviously poses operational risks to the occupants and facility operators. You also have very slow changing operating conditions, stochastic conditions that make it difficult to, that can make it challenging to implement that study. And realistic simulations are a good way around that, but they require building modeling expertise and a lot of effort that takes time and resources in the project as well. So this can limit rapid prototyping of these new control strategies, and then also limit the opportunities from outside experts to basically test new control strategies on sort of the building application because they may not have that expertise either themselves or within their team to model a building in a realistic fashion or something like that. So these are some challenges that we see with controls evaluation in buildings. And so the goals of the BOP test project are to enable benchmarking the state-of-the-art control performance for building energy systems, help accelerate building control software development and deployment, especially including experts from other industries, and then ultimately enable transition and encourage adoption of advanced building control algorithms. So what we ultimately aim for is something like you see on the right there, where you could have a key performance indicator scale and then almost basically be able to benchmark different control strategies relative to each other to start to understand where different strategies perform well compared to others. So the approach here with BOP test is really a complete and open virtual testing environment for control strategies. And it's got sort of three main components here. One, a deployable controlled software runtime environment that basically is able to control all the parameters of the simulation of the case study, so that we know we're comparing controllers on apples to apples, sort of apples to apples way. Create a repository of reference test cases with emulator models and boundary conditions all included that are available to the public to basically be chosen and run within this runtime environment. And then calculating standardized key performance indicators sort of within the framework to make sure that basically it's the same performance metrics calculated in the same way for every case. And the way conceptually this framework is used is a user can deploy the testing software, this runtime environment, which I'll talk a little bit in more detail in a second. You can then use that to basically choose from available test cases, and then basically through co-simulation, be able to simulate basically interact with that test case, that virtual building, with your control strategy as closely as possible as you would to a real building. And then based on the data that's generated during that simulation test, then we calculate basically a KPI report that is able to be provided to users. So that's the general framework. We have a homepage there at boptest.net. We have a GitHub repository there where we do our open source software development, and then there's a journal paper that lists there for more details as well. So just to talk a little bit about some of the framework components. So first, I'll just start with this runtime environment. So basically, it's a Docker container that a user can basically build locally, or we could also be built in the cloud that uses the functional mockup interface for simulation management. The use of Docker allows for rapid, repeatable building and deployment of the simulation runtime environment. And then what we basically do is expose an HTTP RESTful API that has a pretty basic set of functionality that a user could use to interact with the virtual building with their controller. So for instance, through the API, you can do things like receive the available measurement points that are available in the virtual building, the available control points, inputs that a user could say write to within the building using their control. Set up different test scenarios that we define based on the virtual building that's chosen. You can initialize the simulation at particular points. You can set the control step, or basically the simulation step that's taken each time. Forecast, so we actually provide forecasts through the API. So for controllers like NPC or reinforcement learning or other predictive controllers, you're receiving basically the same forecasts as everybody else. You can advance the simulation forward with control signals. You can get results of basically historic point trajectories for all the available measurement and input points. You can receive KPI values, those are those key performance indicators, and then you can actually submit those results to an online dashboard that we're developing as well. So the API has standard return formats, and then we've also developed interface wrappers. For instance, an OpenAI Gym interface wrapper for reinforcement learning controllers, and then we've also prototyped a sort of BACnet interface that's actually being presented at the Build conference in a few weeks. So that's the runtime environment. The actual emulators themselves are high fidelity models with embedded baseline controllers that are written in Modelica and exported as FMUs. So these use mostly the validated libraries that are extended from the Modelica BIPSA library. These FMUs also include all the boundary condition data that's needed to run the simulation and also calculate KPIs, so things like weather, schedules, electricity prices, even carbon emission factors, so that we know that those KPIs are calculated appropriately. We enable the ability to override models at both the supervisory or local loop control points. So you can override set points, for instance, zone temperature set points or static pressure set points or things like that. Or you could override fan speed directly if that's what your controller requires. We try to make the control and measurement points available to a user practical. So for instance, you wouldn't get like unrealistically available measurements, for instance, like internal wall temperatures or something like that, that a controller wouldn't normally have access to. All of the emulators come with documentation, and we try to make that documentation as complete as possible, so you don't, as a user, need to go into, say, the Modelica model and really understand how it's implemented, but you can design your controller from documentation. And then through the BIPSA project, we have sort of a peer review process where these emulators go through peer review before actually being integrated in and made available on our repository to help ensure quality control and also just robustness of simulation and things like that. So we have a number of emulators that are planned and are completed and also still under development, but you can see there's a range of building and system types there between hydronic and air systems and single zone to multi-zone. Right now, the emulators that are available in our repository tend to be on the simpler side to start, but we're working on getting more complex emulators available, for instance, 10-zone, 15-zone models soon. And in terms of the KPIs, so yeah, there's always a lot of discussion in terms of the best way to evaluate control and performance. We have so far come up with a number of KPIs, but these 9 that you see there are those that are actually implemented in the framework. And we don't try to assume that there's one single KPI that will like absolutely rank controllers, because depending on your application or depending on actually your what you're trying to evaluate, different KPIs may be yet more important in certain situations. But all these KPIs are calculated by the software based on the simulation data that's generated. We also define testing scenarios. So what we call test cases are basically like building types or buildings and systems located in a specific climate. But that's not always enough to define like an actual test. You also want to define what time period you run that test for. So is it, say, in the fall or the spring or the winter time? And then let's say an electricity price profile, if it's dynamic or highly dynamic or just constant. So we have some additional scenarios that you can kind of vary based on the building type, or I'm sorry, in addition to the building type. If you needed to calculate custom KPIs, you could, because we do make the data, like basically the data trajectories of the measurement and control points available through the API. And as I mentioned before, we have this online dashboard as well that we're looking to track KPIs from different test runs. So I just want to show overview, a little bit of example usage, and there's sort of a lot on this slide, but I'll just start with the upper right, where there's a diagram of one of our systems that's available in our repository. It's known as sort of the best test hydronic heat pump system. It's basically a single zone model with a radiant floor heating system served by an air source heat pump. And there's basically a distribution pump that kind of circulates water through the floor back to the heat pump. And the basic embedded control within the model, and that it sort of comes with the emulator, is basically a thermostat control that then controls the heat pump compressor speed to kind of heat up and cool down the water that flows through the floor. As a user, you can override the set point, basically the zone temperature set point, or you can also override the compressor speed to control the heating provided to the water. And so what this is showing on the left is a study that was done by Arroyo et al. In K. Leuven. And you basically see two columns of plots there. On the left is what's known as the peak heating period. So that's one of the time period scenarios that we have available for this model. It's basically a 2-week period that covers the peak heating period of peak heating load. And on the right side is a more like typical heating period, which is a 2-week period that covers more of a sort of medium level heating load. And then each row is one of 3 different electricity price profiles, whether it be constant electricity pricing, dynamic, or which might be like a time of use pricing, or highly dynamic at the bottom. And on the x-axis is basically the operational cost KPI, basically energy cost, and then on the y-axis is sort of the comfort KPI, the thermal discomfort KPI that we have calculated. And what the study did on the left was basically test a number of different reinforcement learning algorithms, and also MPC implementations, and sort of compare them all on this test case, and sort of plot them, as you see there. And I'm not going to get into details of the different algorithms that were run, but one thing that's interesting is the MPC tended to perform better. Those are the gray dots that you see more towards the lower left. But my main reason for showing this plot is there's another group at a different institution that actually took the same emulator and then ran sort of their own simulation, or ran their own tests with their own reinforcement learning and MPC controllers. And that's what you see in the lower right there. Basically, we're able to directly then compare their results with the former results, because they're using basically the same version of BOP test with the same emulator, the same testing scenarios. And that's really the main purpose, I think, illustrated of why we're developing BOP tests, to be able to do these types of comparisons, understand what the advantages and disadvantages of different algorithms. It's another example. Having these emulators available, to be able to be rapidly accessed and run through the Docker environment also has some potential for training opportunities. We've run 3 workshops, actually, one of them through a BIPSA building simulation, one of them through a company called Energyville out of Belgium, and actually running a class at the Climate Change AI Summer School, where we used BOP test. And we basically had a number of participants able to access BOP test through the cloud, and actually kind of we had them take some default control that we had in the emulator, and actually we used the same emulator that I just showed before. And then they did some adjustment to the control in terms of changing set points or things, and tried to sort of improve the KPIs using BOP test. But this, again, could be a good way, say in classes or training exercises, to have the ability to basically interact with realistic building simulations. So that's an overview, just some conclusions and next steps in terms of where we're going. So why Modelica for the BOP test cases? Well, it offers opportunities for high fidelity building systems modeling and realistic HVAC network pressure flow and control dynamics, which is really important for these models. Realistic representation of control points available, including supervisory and local loop control. Flexibility in terms of the use of variable time step solvers that allow for smaller or variable simulation step sizes, and the availability of open source validated component libraries, especially those developed through the BIPSA Modelica community, which we use. So a key takeaway, I think, for the Modelica community with this project that I've kind of thought about a little bit is that Modelica doesn't always need to be sort of the end user facing technology ultimately, which assumes that like all the users then need to sort of climb that learning curve of Modelica, which sometimes, depending on your expertise, can be difficult. But Modelica can also serve as a fundamental technology to sort of new modeling use cases that then reach a broader audience. So for instance, a lot of the reinforcement learning control experts don't know physical modeling, let alone Modelica. And so this kind of offers an opportunity for them to access realistic simulations of buildings to test their algorithms. And so I think Modelica can serve as a great engine for this, as long as we're basically embedding good expertise within our models and making sure they're robust, things like that. So in terms of our DOE project, we have some looking forward over the next 3 years. We have new industry partners we're excited to work with, ARUP and Johnson Controls. We'll be concentrating on developing the framework further to enable, say, backnet communication on the interface instead of just using HTTP, and also semantic modeling. So for instance, having the emulator come with a brick model or an Azure 8223P model or something like that to allow for metadata. Additional scenarios representing more realistic building operation. We want to continue to improve and ensure robustness of and stability of our simulations, finalizing emulators, and continued maintenance as in response and feature development in response to users, of course. And we're also looking to continue the BIPSA project. So BIPSA project 1 ended. Pending board approval still, but we're aiming to start a new BIPSA project that focuses on BOP tests to continue the international community development and engagement. And there's 4 main tasks there. Continue to engage with the community, user community, continue to develop the software methods and infrastructure pertaining to sort of the simulation environment itself, develop new test cases for, say, additional building types or applications, and do some control benchmarking of our own. So with that, thanks for your attention. I'm happy to take questions now, or feel free to get in touch. Thanks. Yeah, so the question was how we consider the thermal mass in the test cases and whether we only consider low thermal mass or also high thermal mass. Yeah, so it's a good question. So first of all, the way we consider from a modeling perspective the thermal mass of the building is how in our current test cases, either how the buildings library implements sort of the heat balance method of the room, or the ideas library, which are 2 libraries that extend the Modelica BIPSA library. So basically full heat balance, and including, floor constructions, wall constructions, things like that. There's also an opportunity, and we're working on this as well, to include room models from the spawn of Energy Plus. So there we would basically use the Energy Plus envelope model and incorporate that. So from a modeling perspective, those are the methods that are implemented. In terms of the test cases, and whether they represent buildings with low thermal mass, medium thermal mass, high thermal mass, I think right now, we have say that 2 test cases that utilize floor radiant heating. So there, obviously, the thermal mass of the floor is really important to consider. So that would be sort of like a high mass sort of heating system. The other models I have to think a little bit about, I mean, like there's a 5-zone model that is based on the DOE reference building, and so whatever sort of thermal mass profile you would attribute to that is sort of what we do. So I think it's important to consider the characteristics of the building with respect to thermal mass that's included in each test case, but we haven't specifically said, okay, here's a low mass, medium mass, high mass. Hopefully that helps, yeah.
Thanks for the last presentation. I was wondering if it's would be possible we could set the seat value, but then again, we can
Yeah, that's another good question. So the question for those online was whether or not we've thought about and how we could include uncertainty in these models, both in terms of measurement uncertainty in the sensors and also forecast uncertainty potentially. And the answer is yes. And I didn't get into the details here, so I'm glad you asked that to allow me to elaborate. So it's actually quite a bit of work within IBIPSA Project 1 that's looking at currently how we include forecast uncertainty. So far, we started with weather and in particular outside air dry bulb temperature. It turns out it's kind of difficult when you look at practical MPC or advanced control implementations, how you actually model what that uncertainty looks like in your forecast. So we're trying to kind of characterize that and then embed those methods into bot tests so that then when you sort of call the forecast API, you would get then something with uncertainty instead of the deterministic. In terms of measurement uncertainty, there's you can have sensor bias, you can have sensor noise, all these types of things. We've looked into that as well. It turns out they're difficult to simulate within the Modelica model computationally efficiently. So that's something actually maybe I can discuss with some of the folks here. But in terms of then causing a lot of, like, for instance, simulating noise within the Modelica model causes events, and then that really slows down simulation time. Yeah, there's some computational efficiency issues that we have to think about. So yeah, if people have good ideas, then I think we're all ears as well. I think. Okay, sure. Yeah.
If a user wants to implement this MPC algorithm to your one computing website, and he maybe want to train some models like the weather predictor or some load predictor. So is this a chance for him to get some available data or original model, like IDX model or Modelica model, so he could download it by himself and run the models locally to get some other data?
Yeah, so that's a good question too. So the question was about if there's data available to train models for NPC load prediction or other things like controllers like that. Yeah, so the I'm trying to think. So the emulators that we have available basically come with TMY data. So TMY weather data. The reason I start with TMY weather data is because they're usually 1 year's worth of data. So what we have right now in our emulators is 1 year's worth of weather data available. So you can run the simulation anytime during 1 year period. We define our testing scenarios right now over different 2-week periods. So you could say that if, for instance, the testing period is, I'm just making this up for now, but it's like May 1st to May 15th, then you could use, say, the month of March, run the emulator for the month of March, use that data to train your controller, and then test at your controller how well does it do during the 2-week testing period, May 1st through May 15th. So you can run the emulators outside of the testing period to collect training data to train your models to then run during the testing period. But one thing we do want to look at is how do we make more years available, because some controllers may need more years, or you may want to run an annual simulation or something like that. Yeah.
Yeah, thanks for the presentation. I was wondering if you thought about announcing like a big box test competition so that like you guys like all the developers participate in the competition and then they compare it so that we have like a very nice kind of a very favorite I think, and just that one of your emulators, like we have a small scale at the workshop.
Yeah, so I think so we don't have a one singular competition that we're planning to do. Certainly part of the IBIPSA project has been to sort of continuously evaluate controllers as they're developed. There's IEA Annex 81 on data-driven smart buildings, which I participate in and actually organize. So that's where, so basically, the results on the left were generated kind of as part of IBIPSA Project 1, and the results on the right were generated by a group participating in Annex 81. And there's other groups within Annex 81 also generating results. And so we do plan to kind of write a report from that annex to say, okay, and everyone who used Bob test, here are the results. There's also a project out of Europe called Adrenaline, which is just funded and kind of underway, but they're looking to host a competition of controllers and utilize Bob test as one of the competitions as part of that series. So yeah, we ourselves are not like hosting competitions, but there's people using it.
So I'm going to talk about today I'm going to talk about how we are using these 3D plus models. Yeah, so like in general, agenda, so a few introduction, needs. What was the need for the use to explore this plus models into Swarm and use it? And so for the same needs, we had some previous approaches with tools of features and current workflow that we are using. So technologies, we are using some manufacturing virtual equipment. We have the tool programs chain remotely. So we serve commercial, residential, and transportation businesses. So exactly, the important is we follow the company. We serve different business units and multiple network of services. And I come from modeling and simulation and one of our responsibilities is to work with external partners that deliver those technologies to business units. So that's where I think modeling efforts is a very strong platform where we can address different technologies. Use like physics models, physics models. So Phase 3 Plus is a tool that is developed by training and it is based on, it uses the Dimension Plus simulation engine that is developed by POD and so the really strong point about Phase 3 Plus is that it simplifies model creation for Dimension Plus. So the Phase 3 Plus is slightly different than Dimension Plus Phase 6, where it has integrates all the features of Dimension Plus, and some of the features those have been like suggested internally or the specific customers that we have received. Those new features have to happen. And specifically in this case, these features like building wizard, 3D drawing tool, and building characters, that has a sped up model creation process. Okay, so what are these? So like often like the group I come from that the requirements are experimental and often they are like very level controls. And one of such requirements is that you want to have high fidelity controls related to high fidelity models. Oftentimes, we based on what our objectives are, we simplify one or the other. Like in annual energy analysis, we kind of simplify controls in Phase 3 Plus. But when you want high fidelity controls, as an example, let's say you have multiple compressors and you have multiple stages, and now that model is going to integrate with buildings, high fidelity building. In that case, you really need some tool that can integrate these two high-fidelity models. Yeah, another use case, it's mostly coming from residential. It's that like on one side you have embedded other controls that is being developed similarly, and that model gets used to to create embedded code. And now on the building side, you want to try different types of building, and creating those building models can take long. Creating models and validating them can take some. And the last one is exporting building on the FMUs. So in past we have exported case plus FMUs, but in that case, let's say you just want someone for the data science and activities, we want just building on the FMUs. Our data scientists use those FMUs to generate data. So this is the example that is being shown. Are taken. Yeah.
Sure, there was some internet, the connection, reconnection. Continue.
So realis-simulation offers this language called VR. So through that, we can integrate some advanced controls which are not there in realis-simulation. Now I think there is another one. There's one plugin also there, but very new realis-simulation programs for these to use that option. Controls engineers mostly, like previously having used the access circuit models when data was available to tune RC values. BCBTP and MLE Plus is something that we tried, but so what as our responsibility is that we develop models and hand over to business units. That those approaches never take traction in business units. Whenever building geometries are similar, we develop these models in Modelica. Traceability plus the familiar code, yeah, that's another option that we sometimes take. And the last one is relatively simple, and it works in most of the cases. Is to create a load profile in traceability class, and then feed that into the model. So Spawn, so Spawn was actually Spawn interface was released in the building cycle in last year, and Spawn basically uses another side calculations from Energy Plus and couples the building with intrinsic power, intrinsic components to the model to everything. So there's this excellent paper from Michael how that happens. Michael and several co-authors. If you want to learn more about Spawn, I recommend reading this book. So our target workflow was to create the model in Trace 3D Plus. And create a building using one of the features that one of the options that we have is either through building wizard or through our building model in the 3D tool. or GPX74. Add a plant template. So here, anyway, the spawn the plant template is going to get known. So it's by simply you can add a plant any plant template. And most of in place, most of the options are by default getting an auto site, so you don't need a lot more inputs. Generate an trace idea, and so since the EXCs for Energy Plus and trace, they are slightly different. The same idea we cannot use with Energy Plus. So yeah, we have this ideal conversion process, and then use that in building release library. So that conversion process is something like this. So once you have the base idea, the conversion script kind of looks into what are the objects those are used in the IDL file, and finds that object in the IDL file for place. And also looks at the same definition in Energy Plus IDE. Oftentimes, what we see is that in trace IDE, you have few extra inputs. In that case, we remove those inputs to make it compatible with Energy Plus. Also, in few other cases, there are additional control methods mentioned in the in case. So instead of say 4 by default, like 4 control methods, those are there in Energy Plus. In trace there is 6 or 7. So in that case, if those control options are there in the trace ID, we replace that with default value or default control method definition in the Energy Plus ID. So finally, it's basically is to make that idea of compatibility with Energy Plus. And we run that with Energy Plus. Let's see, make sure that there are no notable warnings or errors. And then there are small changes that you have to make for the workflow response. I think we'd like to comment on the infiltration object from yeah, so this is the very first example that was we created a trace model and an example file from release that we replaced that idea with the converted file. I was not very accurate in terms of dimensions, so that's why you see some differences. But yeah, the results can be managed for that. But this test was just to make sure that this process works. Okay, so this was a recent example of kind of a pilot project where we wanted to see if we can use this for in existing project. So this was so you can see that it's a fairly complicated geometry, and we wanted to test this building with different demand management settings. Here, so fairly general demand management strategies that have been implemented, like depth static pressure reset, and zone temperature resets, and fan speed reset. So from Google map image, we kind of looked that in trace plus extruded trace building geometry, and scale it, extruded building, and applied the process that we discussed earlier, and so this is some of the results that we've shown here. So here we can see that with one of the strategies, there is a sudden as expected drop in the demand. So that this is fine. but the strategy it does see that the demand drops slowly. So that strategy may not be that useful, or you have to start a little bit ahead of time when the request to reduce demand. Other is like strategy was showing that we had shoot up once the demand reduction period ended. So that is something we don't want. So we can focus more on reducing, making sure that when the demand reduction period ends, we slowly get back to normal operating condition. And suddenly, we set back to normal. So so this is like just recent examples where we use this. In conclusion, so this has like significantly reduced the model development time, particularly on the building side. Second one is like integration with controls. So now we can easily integrate the building models that are created in trees with equipment over networks. That is something we wanted to achieve. So current examples are one that's mentioned with demand response modeling. The second one is building on the FMUs. So there is another team who is working on like federated learning, in which they have building models separated from plant different federated learning controller. For that we wanted some way to separate out just the building model, and Spawn has simplified this process for us. And the last one is like what's ease of model sharing and one. So once we have the model in the Modelica environment, now we can take benefit of all the technology to rely on sharing that model, and users can face that excellent to our. So and also we can control it. So before handing over the model, what are the variables that we would like to change? We can simplify and customize these models. So and those features were already there in Modelica, but with the trace now we can integrate a trace building model while delivering this. We would like to acknowledge continuous support from Modelica, Malaysian partners, and Trace development team. That's Matt Distributor, Network Entrepreneur, and Jim Stock, Studio. Thanks.
Is there any and at the moment, like gathering the results in the website and remind the bottom.
Oh, okay. Those are for warnings, just to make sure that actually that was to make sure that I'm not significantly changing something in the model. Like so, since as I said, like, some of the controls those were variations. I was changing that to default values from measure plus RU. So I expect that there will be some the results will change. But those changes are acceptable because we are changing the model. But say my final concern was that am I removing component impact in that process, right? So in that case, the model will not run, or and that's the worst case. That was just to check what exactly I have done. And so that's why I have like another one that has a change log. And there's another extra log. So what I have removed, what I have replaced, that will replace.
Yeah, also, so based on the feature here, how many do that? When you simplify the model, you add model only the 10 minutes period will be different, like the steady states inside of your.
I can't say for sure, but one of the reasons that I had is that the difference is that I was not very careful in terms of generating what was the say R values of the building or of the walls, and yeah, I was not very careful in terms of creating exactly the same model that was there in the building library. So I just looked at like what are the dimensions and square feet area and try to match that.
So I will just repeat what I was said. Maybe you guys didn't hear. So I will start from the beginning. And this is Tao Yang. I'm from University of Denmark. So I'm now in Denmark and trying to present the work. And with the title of comparative analysis of price-based control strategy for high temperature summer storage system. And this work was initially done by my colleague, and I will try to present and try to catch the topic as much as I can. And this work was funded by a European project called Zimport. So with the agenda of this presentation, first I will just present why we are doing this, the motivation, followed by the motivation, and it will be the models of the systems that we develop in demo and trying to implement the control. Afterwards, it will be the simulation setup. So in this work, we have actually developed the model controller and compare with role-based controller, and in combination with some preliminary results. And in the last, I will conclude and point out the future works. So for my presentation, this work is more like a proof of concept, where we develop a very simple model and trying to investigate how this MPC works. For the background, as we know, the energy storage is quite common to be used to balance this energy, or this mismatch between energy supply and the demand. And it is also possible that we can apply some advanced control strategy to improve the energy efficiency for the storage system. And then one kind of the storage is MPC, module control, and it's quite popular to be used in a lot of applications such as buildings, HVAC systems. So, but however, we found that a lot of work for the module control, they focus for the thermal storage focus on the water-based thermal storage, and then the work for MPC application in high temperature thermal storage is still limited. So this work we develop a simple model to prove this MPC can potentially be applied in high temperature thermal storage, and which will be the fundamental or basis for our future work. Here is a picture or diagrams that shows how the high temperature thermal storage works. Basically, it has a rock bed. Basically, it has a rock bed, and then the storage medium will be the air, where you will push air inside into the storage and heat it up to high temperature air, and it will be further used in some heat exchanger to transfer the heat for other applications. This is a like systems that we developed and modeled. It consists of 3 parts: the charging, storage, and discharging. Where so in the charging process, you will the air will be supplied by the fan, and then be heated by the electricity, where the hot air will be stored in this rock bed storage, high temperature storage. During the discharging process, this high temperature air will be further supplied to be used to exchange heat and to heat up the water, which will be used in the Rankine cycle to generate electricity. So in this system, we assume we made a very simple assumption that we assume one uniform temperature in the tank. So in the Rankine cycle, so we also use we also have the district heating that you can use low level low level temperature water to charge the district heating, which can generate some benefit. And then those here there's some equations and the heat transfer equations and the energy balance, which shows the basic associated models. And on the right side, you can see these Rankine cycles. It basically reproduce or like represent these different temperatures at different locations. For this storage, we used the rock from it's a Swedish database, and the volume of this storage is like 1.5 cubic meter with like 2,500 kilograms of rocks. And then this is the size of the tank, and the property of these materials that we use are specified on this table. For instance, you have this volumetric heat capacity, which is quite high, and then you have a density of this Swedish database. Combining with this system schematics, and we developed a simple model in Daimola. And now I will present how we develop this model, how we use this model to develop the MPC and compare with the role-based controller. In this work, we developed a nonlinear multiple controller, and then we also have investigated 3 different role-based controllers, try to compare the performance. This is a simulation setup where we have this high temperature summer storage, and we export it as FMU, and then it will be serving as the emulation model, which will be interfaced in Simulink MATLAB, and then the control part was done using the MATLAB MPC toolbox, where you define the control model, object functions, and within together with constraint and some forecast, such as electricity price and weather, where you take into consideration of the heat losses of the tank. And then following this setup, and then the MPC controller was developed like this, where this is FMU, and the nonlinear MPC controller was present here. And then for the details of MPC controller, it's a nonlinear state model. This control model is a nonlinear state model, and it's also an economic MPC, where the objective is trying to maximize the benefit of this the high temperature submerged tank. So in this object function, you have 3 terms. For the first term, we will have these revenues generated by selling the electricity generated by the Rankine cycle, and also you have the revenues by charging the district heating, but also you have to subtract this electricity consumption, and this is the spot price from Denmark, and then those are the system constraints where you will have this system dynamics, which is a state model. And then in our setup, the temperature of this air has to satisfy within the range of 160 degree to 660 degree, and then the what you control, the manipulated variable is the mass rate of the air, where you can charge and discharge, and the negative value means you discharge in the discharging process, and the positive value means it's during charging process. And we, through some kind of preliminary investigation, we tried the prediction a horizon of 24 hours with a control horizon of 15 minutes. And then now I will present the 3 different controllers we have done. So we initially trying to. So all these 3 controllers are price-based controller. We initially trying to keep it as simple as possible, and then they increase the complexity, and then they find out the better performance role-based controller to be compared with to be compared with MPC. So the initial case where we set up the price threshold with a minimum price and a maximum price, and then if it's below the minimum price, you can charge the storage. Either if it's higher than the maximum, you can discharge. Then if it's within the range, then you have to you will choose to stop it. So you will end up 3 mode. But we found out this is actually not sufficient to control this storage. Therefore, we also take into consideration the comparison, the difference between the storage temperature with its maximum and the minimum temperature, and also take into consideration just trying to observe what was the previous step, what it was that charging or discharging, and based on this situation, we end up with 5 different operation mode, and eventually this lead to this the last controller, role-based controller 3. You have 5 operation mode as well, where you can charge, discharge, and keep charging, keep discharging, or stop. And then within this trial and error process, we defined this price threshold where they showed here with Danish kroner per megawatt hour, and we compare this total net revenues for those 3 role-based controllers. It turns out the role-based controllers 3 generate the best performance among them. Therefore, we will use the role-based controller 3 to compare with MPC. So this is some the preliminary results. So in this plot, you will from the top to the bottom, those subplot as the storage temperature ranging from 100 to 600, and you have the median subplot is a mass rate, charging or discharging, and this is electricity price, where you will it's incorporated from the forecast, and then we compare the role-based control with MPC. As you can see, this is KPIs. As you can see that MPC generates better performance in terms of having a higher net revenues, and then this is and you can also see that in our control setup, we assume that charging and discharging cannot operate at the same time. So you can either charge or discharge for once, and then this shows how the MPC can the mass rate of charging and discharging can vary within the range, but for role-based controller you can either charge or discharge with maximum mass rate, and you can see this frequent the fluctuation of this mass rate in MPC cases, which shows that MPC trying to forecast this, trying to take into try to consider the forecast and trying to maximize the profit. So to conclude, so this is, as I said, this is a proof of concept, and the preliminary result shows that MPC can somehow outperform the role-based controller. However, as it's very related to this choice of the electricity price threshold. If you choose different threshold, it might end up different result. And therefore, for this case, our future work to continue this work is that we would like to cooperate with our industry partners to get more data where we use to develop a more detailed elimination model in Daimola, and then Also, we will investigate how this robust this price influences robust controller to try to find what could be the optimal robust controller and try to see how it compares with MPC. Thanks for your attention. Let me know if you have any comment or questions.
Any questions from audience?
The question was, what is the material in the thermal storage?
So we have a rock back. This is a material of the rock, and then we use air in the storage.
The question was, what is the simulation timing run?
Say it again, sorry. Could you repeat the question?
Yeah. I mean, what's your sampling time and your prediction horizontal time for your MPC?
The prediction horizon was 24 hours. The control horizon is 15 minutes, and we see in our scenarios we simulated 7 days to demonstrate.
Okay, thank you.